Okay, so what we have here is an air nozzle and an adiabatic air nozzle. So of course, an air nozzle takes pressure, power, and internal energy, in other words, enthalpy, and converts it into into kinetic energy. So we have slow moving air coming in on the right, on the left. So out here we have VEL1 equal to 50 meters per second. By the way, the pressure at the inlet is equal to 300 kPa. Okay, so we have incoming air with a certain velocity and pressure, and the air exits the nozzle. So the area is being reduced. Exits the nozzle to pressure equal, so P2, that's at the exit, location 2, 100 kPa. And an outlet velocity, VEL2, of 320 meters per second. 320 meters per second. So the velocity is increased by over a factor of 6 between the inlet to the outlet of the nozzle, okay? So this nozzle is increasing the velocity of the flow. Now we're also given, besides that it's an adiabatic nozzle, we're given some temperatures here. The temperature at the inlet, T1 is 350 degrees Kelvin. All right, so we know the inlet temperature, pressure, velocity, and we know the outlet pressure and the outlet velocity. What are we supposed to find? We're supposed to find the outlet temperature, T2. So we're supposed to find the outlet temperature, T2. Presumably, we're going to be converting internal energy and pressure power into kinetic energy. So presumably, the temperature will fall. Okay? Internal energy increases with temperature, so it goes down with decrease in temperature. So we should be cooling the air as we accelerate it to a higher velocity. Also, the inlet flow area, this flow area right here, this inlet flow area, area 1, is given at 0.01 meters squared. I want to know what the outlet flow area is. I want to know what area 2 is. How large does the outlet circular flow area have to be to accommodate the mass flow through the nozzle, okay? After all, pressure and temperature are going to be different from the inlet to the outlet. So density is going to be different, and velocities, of course, are different. So we're going to need different flow areas, and we'll see this when we do the calculation. Let's see here, assumptions. We'll write those as we go along, okay? All right, let's proceed to analysis here. So we want to find the outlet temperature for the airflow through our nozzle. We want to know what the outlet temperature is. We'll worry about the flow area later. So what's the outlet temperature? Well, if we knew some kind of property at the outlet, a specific enthalpy, an internal energy, and we assumed ideal gas behavior, it is air after all, we can probably assume ideal gas behavior, but maybe we should check to make sure that the temperatures and pressures give us a Z value, a compressibility factor close to 1. So if I know the enthalpy, specific enthalpy or internal energy at the outlet, I can back out from air tables what the temperature is, okay? So somehow I need to get the outlet enthalpy or an internal energy. So analysis. Well, clearly the equation which has enthalpies in it is the energy balance. So let's apply the energy balance to our nozzle and see what we get. E balance. So what's the motivation here? The motivation is if I know an H or a U, I can get a temperature at the outlet. I know an H or a U, specific internal energy enthalpy, I can get a temperature from a table. Okay, so we need to get U or H. Let's apply the energy balance to our nozzle. Let's apply the energy balance to our nozzle. Let's define our system. Let's define our system here. So our system is going to be the area or volume inside of the nozzle, which contains our airflow, okay? Notice that we have air flowing across the system boundary in two places, the exit and the inlet. So we got one inlet, one outlet. Okay, so let's write down the energy balance. Closed system or open system? We have an inlet and an outlet. It's going to have to be an open system energy balance. Q dot minus W dot is equal to dECV dt, time rate of change of energy within our nozzle, plus the sum of m dot H plus PE plus KE summed over all outlets, minus the same thing summed over all inlets. Okay? Let's go through each and every term in this energy balance to see what we can get rid of. First of all, we're told it's an adiabatic nozzle in the givens. So Q dot is equal to 0. 0, adiabatic. Okay, it's adiabatic nozzle. Let's go over here to our schematic. Let's go over here to our schematic and indicate that this is insulated. So I'm going to put some insulation around my nozzle. No heat transfer. It says it's adiabatic. Adiabatic means no heat transfer. Okay? Also, do we see any wires in here or shafts? Any wires or shafts? Or so if there's no wires or shaft, there's no shaft power or no electric power. Also, the nozzle isn't changing shape, presumably. So that means volume isn't changing shape. So that means no boundary work or power. So the entire work term is equal to 0. Evidently or apparently, okay? Okay, left-hand side is completely 0 now. What about the time rate of change of energy within our nozzle system? Well, if we assume steady state, we don't have to worry about the nozzle increasing or decreasing in the energy inside. And I can get rid of this term. So let me assume steady state operation. Nothing changes in time. It's a steady state problem. So steady state. So I'm going to assume steady state. I'll just put SS there, okay? No time rate of change in energy within the control volume. Okay, we have one inlet, one outlet. So let's write down what we have. One inlet, one outlet. Let's see, so this is m dot. So we got 0 equals m dot out, which is at location 2, H plus PE plus KE at location 2, minus m dot at the inlet, which is location 1, H plus PE plus KE at location 1, which is the inlet. So all that stuff, one subtracted from the other, is equal to 0. Let's see if we can whittle this away or whittle this down a little bit further. What's the relationship between the mass flow going in and the mass flow going out? M dot 1 and M dot 2. Single inlet, single outlet, steady state. That means M dot in has got to be equal to M dot out. Let's prove this. Let's apply the mass balance. Let's apply the mass balance to our nozzle so we can prove this. So we got mass balance. Time rate of change of mass within our control volume is equal to the sum of the inlet flows minus the sum of the outlet flows. That's mass balance or mass conservation for our nozzle. Steady state, so there's no change in mass inside of our nozzle over time, so that goes to 0. Single inlet, single outlet. The inlet is at location 1, so I have m dot 1, and the outlet is at location 2, so I have m dot 2. So this implies 0 equals m dot 1 minus m dot 2, which implies m dot 1 is equal to m dot 2. The inlet flow is equal to the outlet flow, so I'm just going to call them both m dot. The flows are the same. So both these m dots are the same. I'm just going to call them m dot now. They're the same. And I can divide both sides of the equation by m dot and cancel out the m dots. So now I'm just going to cancel them, okay? Left-hand side is 0, so I can divide both sides of the equation by m dot, all right? Now the m dot's gone. Let's look at some of these terms inside here. So let's rewrite this equation. I'm going to group together the enthalpy terms, the potential, and the kinetic energy terms. So I have 0 equals H2 minus H1. So I'm grouping together the change in enthalpy, the H2 minus the H1. The m dot's gone. Plus PE2 minus PE1 plus KE2 minus KE1, okay? I'm just grouping together the kinetic potential and enthalpy terms. This change in potential energy of the flow, this has to do with the average height of the flow or position of the flow. That nozzle there, we look back at the nozzle, the average height of the flow is not changing. The average height of the flow is not changing. And typically, as far as forces are concerned, changes in potential energy of something light like air. Maybe not water, but certainly light with a low density like air. Usually the change in potential energy terms are quite small. But in this case, there's no change in average height between the inlet and the outlet flow. So we're going to neglect the change in potential energy between the inlet and the outlet of the flow. So delta PE as the flow goes from the inlet to the outlet, I am going to set that equal to 0. Delta PE from 1 to 2 is equal to 0. That delta PE here, this is delta PE from 1 to 0. PE2 minus PE1. And I'm going to set that equal to 0. Okay? So this term is gone. All right? Now I want an outlet temperature, which means I really want an outlet enthalpy. Outlet enthalpy, specific enthalpy, if I get that numerically, I can go to an air table and back out a temperature. So let me solve this resulting equation for H2, the outlet specific enthalpy. So from our E-balance and application of conservation of mass, I have H2 is equal to H1, specific enthalpy. So I'm going to take the H1 and put it over here. I'm also going to take the KE2 minus KE1 minus KE2 minus KE1. I'll take this term and these terms, put them over on the other side of the equation, and then flip the whole equation. And I have H2 as a function of the inlet enthalpy and the change in kinetic energy of the flow. Now H1, specific enthalpy at state 1. Let's see if I can get that. So H1 is equal to the specific enthalpy of air evaluated at T1. Now, where do we go to get this? If I assume ideal gas behavior, maybe I better write that down. IGB. If I assume ideal gas behavior, I can go, now just give me a minute. Let me see if I can open up the notes here. Just give me a second. Okay. Okay, so page towards the end. Let's see if we can find IGB air property tables. Ideal gas, no. Ideal gas saturation tables. Ideal gas properties of air. Temperature, enthalpy. Okay, my inlet temperature, T1, is 350 degrees Kelvin. 350 degrees Kelvin, 350.49 is the specific enthalpy for my air, okay? 350.49. Okay, 350.49, there we go. All right, so we have H1. What about the change in kinetic energy of the flow, KE2 minus KE1? Well, KE2 is 1/2 velocity 2 squared, and KE1 is 1/2 velocity 1 squared. I have both these velocities, okay? I have both these velocities. So H1 minus, I'm going to factor out the 1/2, and then I have velocity 2 squared minus velocity 1 squared. Okay, and I have all this stuff. Let's plug in, let's get H2. Let's see here, 350 is my specific enthalpy at the inlet. And then I have minus 1/2 outlet velocity. Outlet velocity is 320 meters per second. And that's got to be squared. The inlet velocity is 50 meters per second, yes. And that's got to be squared, okay? Now, one little thing before we proceed. When you have these kinetic energy calculations in the energy balance, the unit on enthalpy is usually kilojoules per kilogram. The unit on kinetic energy, it's going to be an energy per unit mass. This term here, this has units. This quantity here has units of meters squared per second squared. It's actually a joule per kilogram. If I multiply meters squared per second squared by a mass, I get a joule, which is a unit of energy. Think kinetic energy, 1/2 mv squared. If I have simply a velocity squared, I have a joule per kilogram. The unit on these kinetic energy terms, which is the velocity squared terms, has units of joule per kilogram, whereas the unit on the enthalpy, specific enthalpy, is kilojoule per kilogram. So when you do calculations involving kinetic energy, you need to convert the joule per kilogram into a kilojoule per kilogram, especially if you have an enthalpy or some kind of other property in the equation. So I'm going to, let's see, convert this into a kilojoule. So 1 kilojoule is equal to 1,000 joules. Okay? And so the joules will cancel out here, and I'll get kilojoule per kilogram. Kilojoule per kilogram. Let's see here. Let me crank out the specific enthalpy here. Let's crank out the specific enthalpy here. Let's see here. We have 320 squared minus 50 squared. Divide by 2, divide by 1,000. And then 350 minus that is going to be our enthalpy. So I get 300.5 kilojoules per kilogram. My outlet specific enthalpy. My outlet specific enthalpy is 300.5 kilojoules per kilogram. So H2 is 300.5 kilojoule per kilogram. Now, if I go to a table, my air table, let's see if I can find the temperature associated with 300 kilojoules per kilogram. Let's see here, 300 degrees, 300 kilojoules per kilogram. I'd say the outlet temperature is about 300 degrees. By the way, for low temperatures, the specific enthalpy for air is approximately the same numerical value as the temperature in Kelvin. That works for low temperatures. If you go to higher temperatures, let's say 2,200 degrees Kelvin, the specific enthalpy is 2,500, not 22. So I'd rather you didn't use the rule of thumb to estimate H as a function of T by taking the same numerical value as temperature. I'd rather you actually came to the table and extracted out the proper specific enthalpy, okay? So we have an outlet temperature of 300 degrees Kelvin from tables. So T2 is 300 degrees Kelvin. And all this is from table, what is it? What's the air table? I don't know what it is. B11. B11. Okay? You could have also done this problem assuming constant specific heats. You would have had a delta H. Earlier in the energy balance, you had a delta H term, H2 minus H1. You could have substituted in Cp delta T. And if you assume constant specific heat, you do that, you can extract out T2 fairly quickly without using tables. All you need is a specific heat evaluated at some representative temperature, okay? So outlet temperature, 300 degrees Kelvin, okay? So we started off at 350. And the temperature goes down to 300 degrees. So temperature fall, why? Why did it fall? Because we're converting internal energy and pressure power into kinetic energy. It cooled as it accelerated. Let's calculate the outlet flow area, A2. How large does this area have to be for the air to flow in and then flow out? Okay? Well, clearly this is a conservation of mass problem. So how do we know what area 2 is? How do we know the outlet area? So we're going to apply conservation of mass. We already did that, in fact, and we found out that the inlet flow and the outlet mass flow rate are the same. M dot 1 is equal to M dot 2 is equal to M dot. Okay, that was from the mass balance. So to get area 2, we apply the mass balance. And we found that M dot 1 is equal to M dot 2. Now, what's the mass flow rate at the inlet and the outlet? Well, the mass flow rate at the inlet, is equal to the density of the air at the inlet times the flow area times the velocity. You get the flow area times the velocity, you get a volume flow rate. Meters per second times an area, that's cubic meters per second, so you get a volume flow rate. And you go from a volume flow rate to a mass flow rate with density. So M dot 1 is equal to the flow area, A1, the density, rho 1, and the velocity, VEL1. Okay? So flow area times velocity times density, excuse me, looking good, gives you a mass flow rate. So this guy is A1, rho 1, VEL1. Mass flow rate at the outlet is going to be the flow area at the outlet times the density at the outlet times the velocity at the outlet. So let's write what I have. A1, inlet flow area, density at the inlet, times the velocity at the inlet is equal to the outlet flow area, density at the outlet, times the velocity at the outlet. Now, what are these densities? Well, if we use the ideal gas law, we're assuming IGB is valid. We're assuming IGB is valid. I can use the ideal gas law to calculate the densities. So from IGB, pressure times volume is equal to mRT. Density is mass divided by volume. So this implies density, which is mass divided by volume, is equal to pressure divided by RT. Pressure divided by RT. So that's density according to the ideal gas law. So this density here is actually pressure divided by RT evaluated at the inlet. This is pressure divided by RT evaluated at the, inlet. Pressure divided by RT evaluated at the outlet, okay? So let's make our substitution here. A1, pressure RT1, velocity 1 equals A2, pressure RT2, outlet velocity, okay? Via IGB, ideal gas. The gas constants cancel out, so we don't have to worry about plugging those in. That's nice. And I can do a little bit of algebra here, and let's solve for area 2. So area 2 is equal to area 1. And then I got P1 over P2. And then I have T2 over T1. And then I got some velocities. VEL at the inlet divided by VEL at the outlet, okay? Now, I know all these things. I know the pressures, I know the temperatures, I know velocity. Let's plug in. The inlet flow area. Inlet flow area, 1/100th of a square meter. Inlet pressure is 3 kPa, outlet pressure is 100 kPa. Inlet temperature is 350, outlet temperature is 300. Inlet velocity is 50 meters per second. Outlet velocity is 320 meters per second. We have everything. 0.01 square meters. Pressure ratio, 300 over 100 kPa. kPa's cancel out. Temperature, the outlet temperature is 300 Kelvin. The inlet temperature is 350 Kelvin. Kelvins cancel out. And then I've got the inlet velocity, which is 50 meters per second. And the outlet velocity, which is 320 meters per second. They cancel out, okay? Units cancel out. All that I have left over is meters squared, which is a unit of area. Let's see here. Let's crank this out. Let's crank out what this final area, flow area is. Hopefully it's smaller than the inlet flow area, else it wouldn't be a nozzle. Hopefully A2 is less than A1. Let's see here, 0.01 times 300 over 100 And then 350 divide by, 300 divide by 350. And then I have 50 divide by 320. And I get 0.004 meters squared. So the outlet flow area, A2, is 0.004 meters squared. Notice that is less than the inlet flow area, which is 1/100th of a square meter. So A2 is 0.004 meters squared, which is less than 0.01, okay? All right? Pretty straightforward, okay? Pretty straightforward.